Welcome everyone for another FLAN talk. And today we'll hear from Clemente Pasti, who wrote his master thesis with Ryan Cotterell at ETH Zurich, and his home university is USI in Italy. And right now he's applying for PhD positions, and his research interests are from languages with a focus on parsing. And today's talk will be on his paper on the intersections of context-free and regular languages. Clemente, thank you for being here today and presenting your work, and you can take it from here.
Thank you. Okay, so yeah, today we'll present this paper that will be presented at EACL 2023. I don't know if you're already familiar with the barrel construction, but I will make a short intro to it. So in 1961, Barrel showed that context-free languages are close at intersection with regular languages. And they give a proof by construction. So they take a context-free grammar that encodes a context-free language and a finite state automaton that encodes a regular language. And it describes a fair grammar whose language is the intersection of the language generated by the input grammar with the language generated by the input automaton. Unfortunately, this construction breaks whenever there is an epsilon transition in the input automaton. So in this paper, we propose a generalized version of the construction that covers this special case. This is the original paper by Barrel. The Barrel construction is not only relevant from a theoretical perspective because it shows that context-free languages are close under intersection with regular ones, but also because several applications in NLP. One of probably the most known one probably is probabilistic parsing. In 2003, Nederoff and Satta took the original construction and which was designed for unweighted languages, and they gave a generalized construction that handles the weighted case. So we have for weighted context-free grammar and a weighted finite state automaton. And specifically, they were interested in a probabilistic context-free grammar and probabilistic finite state automaton. And they used this generalized construction to compute the infixed probability. The result builds on the observation that if we take the automaton that accepts a single string, what we obtain is essentially a tabular parser like CKY or Early's. Another application, which also builds on Nederoff and Satta's result, is human sentence comprehension under an uncertain input, which was explored by Roger Levy in 2008-2011. In this scenario, we have an automaton, which is depicted here for an example, which encodes a noisy sentence. So for this example, the original sentence would be a cat sat, and then we have some alteration of the original sentence. So we have, for example, a deletion here with an epsilon transition or some substitutions. And then they to reconstruct the original sentence or the probability of the original sentence, they intersect this automaton with a grammar that encodes the comprehender's grammatical knowledge or his prior knowledge. But now I will describe a bit better the details of the construction. So we have an input grammar and an input automaton. And the construction builds a second grammar, which has a set of non-terminals that contains these triplet non-terminals, which with a non-terminal of the original construction, which is, so what is originated by the original construction, by the original grammar is depicted in blue, and what is originated by the input automaton is depicted in red. And so the intersection grammar has this set of non-terminals and then a set of production rules that are partially originated from transitions in the input automaton, and like this rule here. And it does other production rules that are originated from the production rules of the input grammar. Or in this case, 5D and 5E. Can you see my pointer or not? Oh,
yeah.
Is it there? Okay, good. And what is important about these production rules here is that they encode the production rules of the input grammar, but they also encode some information about the state of the automaton. And when the intersection is not empty, all these production rules combine together to form a valid derivation in the derivation set of the intersection grammar. If instead the intersection is empty, there will not be any valid derivation. So the construction was designed to handle the case of epsilon production, which is handled by equation 5E, but it's not designed to handle epsilon transitions in the automaton. And another important property is that this construction is structure preserving, meaning that when we take a derivation in the intersection grammar, it is always possible to link that derivation to a specific derivation in the input grammar and a specific path in the input automaton. Here we have an example to show better how the construction works. So all these production rules that you can see here are originated, except this one, this is a special rule that is designed to handle epsilon productions. But all these rules here are originated from a transition in input automaton. And if we traverse from left to right, we can reconstruct a path in the input automaton, the only path of this automaton that we have here. And if instead we drop all the, we drop all these states in the triplets, we obtain a derivation in the original grammar. So as I mentioned, the parallel construction can handle epsilon production, but it cannot handle epsilon transition in the automaton. The authors don't mention this specifically, but both in the paper by Barrelal and the paper by Nadarov and Sata, but they simply define automata that don't have epsilon transition. However, in many real-world applications, we need to deal with automata that have epsilon transition. There are some operation like automata concatenation that insert epsilon transitions, or the Townsend construction that also introduces an epsilon transition. And in other cases, epsilon transition have a specific semantic meaning, like in the work by Levy for the human sentence comprehension, where an epsilon transition signifies a deletion of a word. But what makes epsilon transition different from any other from a standard symbol in the alphabet. The issue is that the construction works by matching character by character the characters in a string generated by the grammar, and the characters in a string generated by the automaton. So in this example, we have two strings that are equivalent, and the constructions, the algorithm start matching characters one by one, but when it reaches an epsilon, it breaks, because of course you cannot match an epsilon with any other character in the other string. So I will show better a failure case. Here we have a very simple automaton and a very simple grammar. Both the language of the automaton and the language of the grammar contain a single string, which is AB. But if we use borderline construction to compute intersection, instead of obtaining AB, we obtain an empty set. And more specifically, what we have is that we have this is a broken derivation in intersection grammar. So we have this transition here that is encoded in this production rule, but we didn't have a technique to handle this epsilon transition here. So when we get here, the construction breaks because it cannot cover this span from Q1 to Q2, and so at the same time it cannot produce anything that cover this other transition. So the construction breaks, and there are no valid derivations. No valid derivations in the intersection grammar. And so we designed a generalized construction. So I was working on my master thesis, and I was designing a new parsing algorithm. And to do this, I had to concatenate two automata and then perform the parallel construction. And while I was doing this, I realized that the construction would break. And so we came up with a new generalized construction that can handle the special case. The rules that what has been modified with respect, this is the original construction, and on the left and on the right, the generalized construction. What is different has been marked in blue, and we have actually three new set of equations. Equation 6G cover any epsilon transition that is not right before a final state. And as you can note, they are right branching. And then equation 6B cover epsilon transitions that are right before a final state. And then equation 6C is just an Elper equation. I will show this a bit better with an example. So now we have the example that we had before of the automaton with an epsilon transition and our context for grammar. And by using this rule, we can generate this derivation structure here that you can see here, that basically patch this epsilon transition. It has weight 1, so it doesn't change the weight of the intersectional language. And what is important about this is that it can cover any sequence of consecutive epsilon transitions. Because if you consider this example, for instance, we have a potential infinite number of epsilon transition, But this production rule here generates a right branching structure that can cover any epsilon transition, as you can see here. But so as you can see, and if you have any question, please interrupt me, because I know this is a bit complex to understand maybe. So if you have any question, please go for it.
Can I ask a question?
Yeah.
So my understanding is that if you compare this tree to the original tree, you're basically always inserting the epsilon transition, like in next to the next occurring token. Like you're kind of you're creating this structure where like this like B, that you have two nodes corresponding to B, and then one of the children of that node, it corresponds to the epsilon transition that precedes the B. Is that the right intuition?
Exactly. Yeah.
Okay.
And the well, the interesting fact is that so one thing of the parallel construction is that if you look at the states of the non-terminals of the triplets on the right hand side, the states always have to be matched. And this is also the intuition of why the parallel construction is essentially a tabular parser. And yeah, and as you can see here, so we keep counting the epsilon transitions, and we start from Q1, and then and here's we have this plan that goes from Q0 to Qn, and step by step we consume all these transitions basically. No, wait, let me move a bit because okay. Any other questions?
So how does the epsilon transition to a final state work?
Yeah, that's the interesting part, because of course this works only if we need to have a terminal symbol on the right, because otherwise we cannot make this trick. At the same time, we could not make a rule that was both right branching and left branching, because otherwise we would have overcounting. And so what we did is that we designed another production rules with a modified start symbol that instead of being right branching is left branching, and that it covers epsilon transitions right before a final state. Here we have an automaton, an example automaton. Maybe you can zoom a bit, I don't know. You can see. So what happens is that we start with the start symbol, then it can only produce a triplet with the with an S with the tilde, and then it starts covering all the epsilon transitions, and when it has finished, it converts to the standard S, and it cannot anymore go back, and we have a standard derivation. So it was a bit of engineering, because at the beginning we had not realized this issue here, but I think it was I originally came up with this. I think that then was Jason Eisner that realized this problem with the epsilon for a final state. So we added this to handle this problem. And okay, any other question? Then we can go forward. Okay. So now I will briefly discuss the size of the construction. So of course there are some other rules that are complexity, but what is important is that the asymptotic size of the old construction is the same of that of the generalized construction. And that's because the rule with the highest asymptotic size is unchanged from the original construction. And in the specific case of a binarized input grammar, we have that both the original grammar and the improved one are cubic in the number of the states of the automaton. So here we have again a bit the two construction paired together, and this is these are the production rules with the highest cardinality, which is depends on the size of the biggest production rule in the production rules. But these rules are unchanged. So of course there is some some overhead, but in terms of asymptotic size, it doesn't change the size. One last observation, because probably you might think that why should we do something that is so complex when we could just do epsilon removal on the automaton? And it is true, in many applications, we can use epsilon removal using, for example, techniques that have been described by Maury or other authors. But the issue, I mean, for many applications, that is a good solution, but the issue is that the original barrel construction, when applied on an automaton that is not that is epsilon free, is structure preserving, meaning that if you take a derivation in the intersection grammar, you can always reconstruct a path in the input automaton and a derivation in the input grammar. And this is relevant, for example, for parsing, because if you want to reconstruct, if we think a simple case of a straight line automaton and we want to use the construction for parsing, then you can reconstruct a derivation in the original grammar. But if we perform epsilon removal, then we're not able anymore to reconstruct a path in the input automaton. And because epsilon removal is not a bijection, basically. So there are many automata with epsilon transitions that can be mapped to the same epsilon free automaton that represents the same language, but it has a different structure. And so in many situations, the arcs of the automaton have a specific meaning. So it's interesting to be able to reconstruct path in the original automaton. So if we take, this is an example derivation again of the I think I already shown this, but in the intersection grammar. And if we traverse the pre-terminals from left to right, you have Q0, Q1, Q1, Q2, and Q2, Q3, and then here we can recognize how many loops we have taken of this in this automaton here, because we can just count them. If we would simply perform epsilon removal, we would lose this information. And again, if we drop all the states in the triplets, And then of course we also need to cut here, but then we can obtain the original derivation in the context-free grammar, in the input grammar. So if you have any questions, it was a brief presentation, but I can go deeper in the details if you want.
So I'm curious about the role of determinism in, I guess, both the original Bar-Hillel construction and in your modification of it. So like the example you showed was a deterministic automaton, but does it work if you have non-deterministic arcs as well?
Yeah, it works. Well, an automaton with epsilon transition is not
Fair, I guess. Yeah.
deterministic anymore.
Well, I mean, this one in figure A is because there's only one arc out of Q1. But you're right. Like, yes, if you have two arcs. Okay.
Because if you consume D, then you
Yeah.
could be both Q1 and Q2. So it's not deterministic anymore.
Okay. Yeah. Right. Okay.
But what is important is that the information is not that much encoded, but in the terminal that it's in the triplet by the states that are in the triplet, and this is how you can reconstruct the path.
I see.
Because you Q0, Q1, Q1, Q2, and then so you can reconstruct all the transitions that you have taken.
I see.
Yeah, I think
So I
it's
guess
the eventual CFG parser is what would assume responsibility for the non-determinism.
Yeah. So wait, because you're referring to the fact that we can use the bar for parsing, right?
Right. Yeah. So if you want to build a parser,
so I
let's
will
say,
show the like the standard example because I think it's easier for understanding. Yeah, this is like without like the very simple string. So suppose that we want to parse this string, and then what we have is that if we remove all non-generating and unreachable non-terminals, we have basically a tabular parser. So we have all, if we take like a chart with these are the index of the string, this become like 0, 1, 2, 3. Then we have that this entry is filled only if there is a derivation for that starting from this non-terminal that spans from position 1 to position 3 in the input. So this is the idea of why it can be used for parsing, basically.
I see. So let's say that because of non-determinism, there was like a path from Q0 to Q1 consuming the, and then there was also a path from Q0 to Q5 consuming the. You would have two cells in your table that were filled in by those two transitions, but in terms of reconstructing the final tree, only one of them would show up. Is that the right?
Oh, okay. So you mean how do I reconstruct this tree here?
Yeah.
If I have, okay. So in this case, you need to so this piece here is not relevant for the structure of the tree. This is just some glue that is used to match a derivation with a path. So you need to recognize the situation and of this here. This is the only production rules that contain a terminal symbol. Either they produce production rules that contain a triplet with a terminal symbol, either it's a terminal or they produced a triplet with the epsilon. And if they produce a triplet with the epsilon, then this part is not relevant for the structure of the derivation of the input grammar. So the idea is that you can always recognize what originates from the grammar and what originates from the automaton.
Okay, thanks.
And yeah, we haven't really explored practical applications a lot, but we thought it was even interesting from a theoretical perspective. But there are some practical situations where this might turn useful. For example, if we use if you take a look at the paper by Roger Levy, he's using automata with epsilon transitions, and so it might be interesting in certain situation, even though he doesn't discuss this, and to reconstruct the input the path in the input automaton as you have it here when you perform the parallel. I don't know whether he was just using epsilon removal to fix this issue, or whether he just didn't realize it. But with our construction, you can do this.
Hi, Clemente. So I really enjoyed the talk. This is an interesting paper. So I'm curious, have you actually hooked this up end to end, like hooking up your modified bar Hillel with a CFG parser to get something that parses inputs?
We haven't done much of that because in the standard, so if you want to parse a straight line automaton, our construction is basically equivalent to the original one because there are no epsilon transitions. The situation is different if you want to parse a general automaton. Even this could have different meanings. So if you want to if you think about parsing in a more abstract way, and instead of parsing a string, then you want to parse a regular language, that would be more interesting. Even though we at this level we didn't focus on that, let's say.
Thank you.
Thanks very much for the talk. Could you say a little bit about how the weights interacted with the requirements of your generalization?
Yeah. So I will. So do you want me to discuss the weights in the general case, or just the case of the case for the original construction, or just the weights of the generalized construction?
Just sketching a bit how the weights work in the generalized construction would be helpful.
Okay, so I discussed more the unweighted case when I showed the examples, because that was easier to explain. But first, we assume that when we talk of intersection in the context of a weighted language, what we have is something like where is the paper? Because I don't have it here. We assume that the intersection is something like this. So the weighted language is a mapping from sigma star to to the weights of a semiring. And what we have is that we multiply the weight that one language assigns to that specific string with the weights that the other language assigns to that specific string. And if you take a language over the Boolean semiring, essentially you obtain the standard definition of the intersection, or at least it is isomorphic to the standard definition. So when we look at the production rules here, so the rules that we have added here whole have weight 1, which is the natural element under multiplication in that specific semiring, because they're not directly connected to any transition or any production rule in the derivation, but they're just used to glue together pieces of the grammar, because the weight of the transition is already encoded by this rule here. So we need to keep we assign weight 1 to this rule here because we want to keep the final weight unchanged. And then I will also go briefly about the weights of the other weights in the construction. So this weight here, maybe it's, well, I can explain it here. So first, the start rule. The start rule has to account for different initial and final state. So we multiply a triplet from that contains state qi and state and this other state. Then we have the multiplication of the initial weight of this state and of the final weight of this state here. This encodes rules in CG. We need the weight is taken from the original production rule, and this other rule here encodes transition in the automaton. So the weight is the same of that of the transition. Is that clear? Or
you alluded to the fact that you couldn't allow both left and right branching because you would overrepresent the derivations, which would alter the weights. Is that correct?
yeah. So we had to avoid overcounting, because otherwise we would overcount. We would count double derivation, and that would account for twice for the weight of a specific derivation or a specific path. And because so the idea is that what we want in the end is that we have a situation where well, I can explain it in word, but we have a situation where the weight, so the weight of a derivation is of the intersection grammar is equivalent to the multiplication of the weight of the matching derivation in the original construction multiplied by the weight of the matching path in the input automaton. And that's why we need a bijection, because we want to keep this property. And that's why we need to separate what is left branching from what is right branching, because we need to keep a one-to-one mapping.
I think I got it. Thank you very much.
Yeah, it's a bit hard to explain in words here, but in the it's explained in greater detail in the proof of the appendix.
Mhm.
Yeah.
Thank you.
Okay.
So how would the construction work or generalize if the semi-ring wasn't like the Boolean semi-ring for the weights, but the like string or language semi-ring for like transducers, basically?
Okay. So this only works for commutative semirings because when you again, this is a bit hard to explain if I don't have a figure here to show, but when you multiply the weights of the in the maybe there's a passage on the proof, but when you multiply the weights of the production rules in a derivation intersection grammar, you need commutativity in order to separate on one side the weights that originate from the derivation from the weights that originate from the from a path in the automaton. Maybe I have this here in the proof somewhere. Yeah, here. Yeah, we need to we need commutativity because when this is the weight of the derivation in the intersection grammar. And what we do is that step by step, we rewrite this as the weight of a derivation in the regional grammar times the weight of a path in the on the input automaton. If we don't have commutativity, we cannot rearrange the weights in order to achieve this, basically.
Makes sense. Yeah, that's a clear explanation. Thanks.
Okay.
Do you think that there's a way to extend the construction for like non-commutative semi-rings, or would like the definition of intersection have to change even? Or have you thought about that at all?
So maybe, so I was just thinking about this now. So maybe if you need to specify a specific order in which you multiply the weights of the production in a derivation. So you might be able to do that, but I'm not sure because. So here when we define the weight of a derivation, we don't define the order that in which you need to take into account the production rules. Since it's commutative, you just need to multiply all of them. Maybe there is an order, specific order. So maybe if you first multiply the weights of the preterminals, and that might work, because then you have you can separate what comes from the path and what comes from the grammar, for the automaton what comes from the grammar. Yeah, you might be able to do that. I can think about it and then I'll let you know.
Cool. Yeah. Thanks.
Okay. Yes. I can't hear
Sorry.
you.
Yeah, I know. I said I think I'll end the recording here.
Okay. Yeah. Sure. Yeah.
Thank you for the great talk and the good discussion.